And in order to do that, I will have to now I will actually, instead of just stating theorems in a loud voice, do a little computation in which I compute in a simple term that doesn't involve, a simple way that doesn't involve running around the graphs counting propagators, the superficial degree of divergence of an arbitrary Feynman graph in a theory of this kind. And this will enable us to see the difference between a renormalizable and a non-renormalizable theory. I will need to define some concepts. Fe is the number of external Fermi lines in any graph. Fi is the number of internal Fermi lines. B, to no one's surprise, is the number of external Bush lines. And Bi is the number of internal Bush lines. Ni is the number of vertices of type I, that is to say, coming from the ith term in our effective Lagrangian. Now, I will write a formula for the superficial degree of divergence of any graph, which will turn out to simplify things enormously. Firstly, I'll just write down our power counting. Every internal Bosch line gives a factor of 1 over k squared from the propagator and a factor of d4k from our integration d4k. Therefore, it gives us 2 powers of k in the numerator. Some of those will be reduced by delta functions at the vertices, but I'll take care of that later. Internal. Every internal Fermi line gives us 1 d4k in the numerator and 1 power of k in the denominator. Every derivative interaction will give us 1 power of k in the numerator. I remind you, I've left on the left-hand board di is the number of derivatives in an interaction of the ith type. Now, I've overcounted the internal momenta because not all of them are independent integration variables. Every vertex has a delta function, and that knocks out 4 integration variables, except that these are all IPI graphs and therefore a fortiori connected. There is 1 overall delta function left over for energy momentum conservation. So I've overcounted the number of delta function restraints. This is simply an automatic formula for what I did before when I was counting numerators and denominators and so on. Is this clear? 4 powers of internal momenta for each internal line of any kind, 2 cut down by 2 for Bosch propagator, cut down by 1 for Fermi propagator, cut down by 4 for each vertex, which gives us a delta function, except there's 1 delta function that doesn't restrain the loop momentum and is left over for overall energy momentum conservation. If there is anyone in this room who does not understand this formula, speak out. Just counts the number of momenta in numerators and denominators. In this form, the formula is a mess. Fortunately, we can simplify it by using the law of conservation of boson ends. Every external boson line has one end that ends up on a vertex and one end that is hanging out. That's what makes it external. Every internal boson line has two ends which end on a vertex. That's what makes it internal. Every vertex of I type has Bi boson ends coming on it. This is the law of conservation of boson ends. Likewise, there is the law of conservation of fermion line ends. Thus, by elementary algebra, we may eliminate the factors involving internal lines and only be left with factors involving the vertices and the external lines. I will now do that. I'll first keep track of the external line functions. For the bosons, I get a minus Be, putting it on the other end. For the fermions, I have to multiply 2 by 3/2. Now the factors involving Ni. From this formula here, I get Bi. From this term here, I get, multiplying by 3/2, Fi. From this factor here, which is already up here, I get Di. From this factor here, I get minus 4. And the good thing it's there. Otherwise, everything would make things more and more divergent. And finally, I'm left over with a plus 4. This formula is extremely nice because it tells us how divergent adding an extra interaction of a given type makes a graph. In particular, if I define delta I, which I'll call the index of divergence, equals Bi plus 3/2 Fi plus Di minus 4. I am obviously going to have to introduce a lot of counter terms if I have an interaction in my theory with delta I positive. Because whenever I add an extra internal vertex of that type, I send the degree of divergence up by 1. I have to make more subtractions in my in my Taylor expansion, and I have to add, therefore, a counter term with more derivatives. Okay? Now, I will not say everything I want to say about renormalization here, but I want to do a specific example to show you what's going on. My first specific example will be 5/4 theory. Plus terms involving the counter terms, which I will figure out iteratively by using this formula. There's only one kind of interaction in here at the moment. That's the 5/4 interaction. The number of boson lines is 4. The number of fermion fields is 0. There ain't no fermion fields in the theory. The number of derivatives is 0. Therefore, delta equals 4 plus 3/2 0 plus 0 minus 4 equals 0. Therefore, the degree of index of divergence of this interaction is 0. Now let us compute the superficial degree of divergence. No matter how many internal 5/4 lines, 5/4 vertices we have, I could draw a complicated diagram that would cover this blackboard and run over into the sideboard here. This elementary algebraic counting on this board shows this term is irrelevant. The superficial degree of divergence is determined just by the number of external boson lines. There are no fermions in the theory, so I can forget about this term. Therefore, D equals minus BE plus 4. Thus, I need only consider two kinds of graphs with external boson lines less than or equal to 4 in number. Ones with greater than 4 will always be superficially convergent, and by the Bolovyov prescription will require no counter terms. I have the following possibility. BE equals 0. D equals 4. This is irrelevant. This is a vacuum-to-vacuum graph with no external lines, and we throw them away anyway. Because the theory is invariant, under phi goes into minus phi, I don't have to consider graphs with odd numbers of boson lines vanish anyway. So I need only consider the next case up, D equals 2. D equals 2. This is in general a graph that looks something like this, except of course it's one pi. And we will have to subtract out the first two terms in the Taylor series expansion. Therefore, to any order in perturbation theory, this will introduce counter terms proportional to phi squared, which will cancel the 0th order term in the Taylor expansion with some coefficient depending on how far we've gone in perturbation theory and what the cutoff is, and some term proportional to d mu phi squared. Then I have B equals 4. This has D equals 0. Thus, the only counter term introduced here is to cancel out the value of the thing, and that's C phi fourth, with no derivatives because we only go to 0th order in the Taylor expansion, so we have no powers of momentum. These are new interactions, and for consistency, I should check that they don't change my divergence counting. This is a phi fourth again, so again has delta equals 0. This has two phi's and two derivatives, so again has delta equals 0. This has two phi's and no derivatives, so has delta equals minus 2, which is groovy. That just means I have overestimated the superficial divergence of certain graphs, where they include interactions of this kind. They don't change the divergence counting. Thus, in this theory, the counter term Lagrangian is a sum, or some coefficient I have to compute, of a phi squared, a d mu phi squared, and a phi fourth. Thus, this can be interpreted in our usual way by rescaling the fields, as simply saying we rescale phi to make the d mu phi squared coefficient of canonical form. We assemble the other two terms to define the bare mass and the bare coupling constant. The result, therefore, of Hepp's theorem applied to this example is that in this theory, all observable quantities to any finite order of perturbation theory are independent of the cutoff in the large cutoff limit if the field is appropriately rescaled and if the bare parameters are chosen in an appropriate cutoff-dependent way. Because the terms we have added are of the same form as the terms that were there in the first place. That is what we mean when we say a theory is renormalizable. This is a renormalizable theory. You choose the bare coupling constant in an appropriate cutoff-dependent way, the bare mass in an appropriate cutoff-dependent way, rescale the field in an appropriate cutoff-dependent way, and all the divergences will cancel to any finite order in perturbation theory. Okay? Is everyone happy with that? I want that point firmly in your head before I develop these ideas in the beginning of the next lecture. Everyone happy? No questions? Now, suppose, on the other hand, we had a phi-fifth interaction. Then this has 5 external boson lines. Then whenever we consider a graph with more and more of these 5/5 interactions stood inside of it, the superficial degree of divergence will get larger and larger. We'll have to make more subtractions, and we'll need more and more different kinds of counterterms. Not just the coefficients change order by order in perturbation theory, but their qualitative character. A graph, if we go to a sufficiently high order in the 5/5 interaction, a graph with 2 external boson lines will have the d equal to 1 million. That happens to millionth order in the 5/5 interaction. And therefore, we would have to subtract something with 2 phi's and a million derivatives. Is this clear? This is a non-renormalizable theory. We are off on the unending escalation of ambiguities that characterizes non-renormalizable theories. We need more and more different kinds of counterterms as we go to higher and higher orders in perturbation theory, and they cannot be interpreted as simply a rescaling or redefinition of the parameters that occur in our original Lagrangian. People sometimes say, well, that's just, so what? They say, you've got a prescription that fits those things uniquely. You know the Bogoliubov prescription is unambiguous. It tells you what those counterterms are. But I mean, the Bogoliubov prescription is arbitrary. Bogoliubov invented it to make the theorem easy to prove. You don't have to subtract at 0. You could subtract at some randomly chosen point, often Euclidean space, if you want to avoid all the thresholds and everything. You could subtract different Green's functions at different points. You could subtract the second-order term in the Taylor's expansion about the point 0 and the third-order term in the Taylor expansion about the point 17. You know, the whole thing is just an ad hoc prescription to make the thing run simply. If you have a phi to the 17th interaction produced eventually, or d mu phi to the 42nd interaction produced eventually, then that thing, if it comes out as part of the counterterm prescription, there's no reason why it shouldn't have been there in the original Lagrangian. And a non-renormalizable theory really does, as we said earlier, involve, if you go to sufficiently high orders in perturbation theory, an unlimited number of free parameters. So this is the dividing line between renormalizable and non-renormalizable theories. Whether all the interactions have delta less than or equal to 0, or whether where delta we have this beautiful formula for, or whether all the some of the interactions have delta greater than 0. If you have positive deltas, you are cooked. It is a non-renormalizable theory. It requires an infinite number of parameters to arbitrarily high orders in perturbation theory. It is bad news. I don't know how to make sense out of them. Nobody knows how to make sense out of them. Every few years, someone has an idea about how to make sense of them, and every few years he's shot down. They may be sensible, but nobody knows how to make sense out of them. Now, I have not said all I want to say about renormalization, although I'll let these things sit in your head for 4 or 5 days, and then I'll give another 15 or 20 minutes at the beginning of next lecture, telling you the remaining things. After that, of course, we'll be almost at the end of the semester, but that's an artificial break, aside from those of you who want to drop out. And so I'll just begin the next topic, which will be continued in the second semester, and I will start talking about vector fields. Oh, just a minute. Will those who plan to take